One of the great benefits of having chain maps and induced maps on homology is that we're now able to deal with homological things with functions. And so a lot of the techniques that we used when working with homotopy, which necessarily required continuous functions, are now available to us. So we can play much of the same game, but now on an algebraic rather than topological level. And one of the best tools for doing this is called the snake lemma, which we're going to talk about now. So this lecture is just going to be about the snake lemma and the proof. So we're just going to set things up, and then in the subsequent lecture, we will see some amazing calculations. So the point is, if you find this bit a little dry and not, where's the payoff for all the work we're doing, just be patient and the rewards will come. So remember, when we were studying homotopy, the tool that helped us a lot was an understanding of what the contractible spaces are. And these are the spaces which have the trivial homotopy of a point. Now, on this algebraic level of homology, you can ask what chain complexes have boring homology, the trivial homology, and we're going to get to that next. So here's the definition. A sequence, and let's call it VD. D is bad, let's say A, of vector spaces. They're all over some field F, which I haven't bothered to write down, and linear maps. V0 to 0, then there's V1, so we'll put the map A1 here, A2, okay, and it keeps going. So this is, as far as we're concerned, it's a very long sequence, is called exact if, if the kernel of AI equals the image of AI plus 1 for every I. Now, kernels and images of maps between vector spaces all laid out in a neat little line are going to be super familiar. These are precisely chain complexes. To make a chain complex out of this, I mean, you just have to note that for a chain complex, the image has to be a subspace of the kernel, but here they're literally equal. So of course, it's trivially a subspace of itself with trivial homology. So these are all the chain complexes that have no interesting homology, because when you do kernel modulo image, so kernel AI mod image AI plus 1, you've quotiented out everything, and so you're left with the trivial vector spaces. So these are, from a homological point of view, zero objects. These are the things that there are no interesting homology. Every HI of them, of these chain complexes, which we're calling exact sequences because they're important, so all their homology is going to be 0. Okay, so you may not have seen any examples of such infinite sequences of vector space and linear maps with kernel equal to image outside of, maybe building a chain complex of certain type by yourself. So this is not, this may not be a familiar object yet, but there are simplifications of it that are basically encoding all sorts of interesting linear algebraic information. So here are some examples. And before I get to the examples, let me say these are all going to be examples of short exact sequences. So such a sequence, such meaning satisfying all the stuff that is in the definition upstairs, is called short exact if all but 3 of the consecutive vector spaces. So all but 3 consecutive vector spaces are 0. So it doesn't matter. Without loss of generality, you could just say V0, V1, V2 are 0. So even in this very simplified setting where all the maps, except the ones between V0 and V1 and V2 are forced to be 0, this is going to create some interesting linear algebraic examples. And again, I should emphasize that for short exactness, I'm not saying that V0, V1, and V2 cannot be 0. I'm just saying outside of these three, everything should be 0. So here's one example of a short exact sequence. So let's say you have 0, V1, V2. Sorry, other way around. V2, V1, and that's all you have, right? So everything else is 0. So here, let's take a look at this map. Its image is 0, which means this map's kernel has to be 0. So this sequence is short exact if and only if the map from V2 to V1 is injective, because it has to have a trivial kernel. Okay, next, there's the mirror image of this picture, which is, let's say you have V2 to V1 to V0. So this is going to be short exact. Well, let's see. Instead of V0, I think I just want a 0 at the end instead of 0 at the beginning. Okay, this is going to be short exact when? Well, you have a map. So this second map here, its kernel is all of V1. Everything is being sent to 0, which means this guy's image has to be all of V1, which means the map from V2 to V1 is a surjection. So if and only if the map from V2 to V1 is surjective. Okay, well, so if a leading 0 makes you injective and a trailing 0 makes you surjective, then having both means that you must be an isomorphism. So this map in the middle has to be both injective and surjective, and for vector spaces, that's an isomorphism. A little bit fancier, and that sort of includes A, B, and C as a special case, is you have an honest V2, V1, V0 to 0. Because of the leading 0 and the trailing 0, what you know is this has to be an injection, and that has to be a surjection. So V2 is sitting inside V1 as a subspace, faithfully embedded by the map, and V1 surjects onto V0, and so V0 is a quotient. And the fact that this is an exact sequence means that the image of V2 inside V1 and the part of V1 that gets crushed to V0 are disjoint. So another way of saying this is that this is short exact if and only if V1 is a direct sum of V2 and V0. Now, A, B, and C work in broader context than vector spaces. They're true even if you had a sequence of this type for abelian groups, for example. But D is very specific to vector spaces. Anyway, we're not going to deal with abelian groups. We're only talking about vector spaces. So there's exactness and some linear algebraic consequences of it for you, if you like. Okay, so we're going to use the definition, this notion of a short exact sequence for vector spaces to inherit a notion of short exact sequence for chain complexes. So an arrangement of chain complexes and chain maps of the form, so you have CD, then there's some chain map phi that takes you to C prime D prime, and then there's another chain map psi taking you to C double prime D double prime. Let's emphasize the fact here that it's C double prime. So this is a short exact sequence of chain complexes. That's a mouthful, isn't it? So let's just call it SES from here on out. And if I mean short exact sequence of vector spaces, I'll say something different. But we care about these. So SES means short exact sequence of chain complexes for the rest of the lecture. So this is a short exact sequence of chain complexes if and only if, for every dimension k bigger than 0, the sequence of vector spaces which we write as follows. There's going to be CK, that's a vector space. It's getting mapped by phi k to CK prime, which is getting mapped by psi k to CK double prime. And if you add a leading 0 and a trailing 0, this is exact, is short exact. Okay, this might look circular, like we're using the words short exact in the definition of a short exact sequence, but we're not. We're trying to define a short exact sequence of chain complexes, and we're doing it in terms of short exact sequences of vector spaces at every level k. So that's all it is. So at each level k, each dimension k, you get a short exact sequence of vector spaces. And if you go back to our handy little cheat sheet, we're in scenario D, where the map phi k is going to be injective for every k, the map psi k is going to be surjective for every k, and so ck prime is going to be the direct sum of ck and ck double prime. Okay, so this is the input to the snake lemma. The snake lemma is going to eat a short exact sequence of chain complexes and produce another exact sequence that relates their homology groups. So here is the result. So this is the lemma. It's called the snake lemma. And I will try and tell you why it's called the snake lemma as we talk about the proof. Take a deep breath. Here it is. So for every short exact sequence of chain complexes, let's say CD to C prime D prime as before, C double prime D double prime, there exists a family of linear maps. So linear maps, meaning between vector spaces, these are no longer chain maps. We'll call it dk, going from the kth homology of C double prime D double prime to the k minus 1th homology of CD. And this is for all k bigger than 0. So they're relating the homology of the third chain complex to the homology shifted down by one dimension of the first complex that fit into an exact sequence of vector spaces. So first of all, before showing you the exact sequence of vector spaces, these maps are called the connecting homomorphisms because they connect things. So here's what's happening. So for every k, you have the homology of CD, you have the homology of C prime D prime, you have the homology of C double prime D double prime. So k. And you also have the same story for k minus 1. C prime D prime, H k minus 1, C double prime D double prime. Okay, so these are all going to sit in an exact sequence of vector spaces. Remember, each one of these is just an ordinary vector space, no chain nonsense required. Okay, so these maps are going to be induced on homology by the chain maps that were given to us in the short exact sequence. This is the kth induced map on homology by phi. This is the kth induced homology map of psi. And similarly, k minus 1 level here, k minus 1 level here. Okay, and these dk maps are going to do this. They're going to take you from this kth one and transport you one level lower to k minus 1, and then there's similarly dk minus 1, and something came here. This is the dk plus 1 level. So this is where they fit in, and this whole thing is going to give you an exact sequence of vector spaces. And this is the content of the snake lemma. This is just the statement. It's saying if you have short exact sequence of chain complexes, then there exists some map that will help you put the homology groups of all the dimensions all at once into a long exact sequence. Again, right now, we just want to construct dk minus 1, dk, dk plus 1, and so forth. This will be useful even if it's not obvious why right now. Okay, so we're going to give an outline of the proof here. It's a slog. It's a lot of algebra that some people really take to, other people are scared of. And I don't want you to be scared of it. I just want you to sort of breathe it in. This will not be on the exam wherever you are watching this. There's no exam. Okay, so let's see. How should we prove this? I'm going to give the construction of dk. There will be lots of different steps. Not all of them will be justified. They can be justified. But here's the basic idea. So is to look at the chain complexes and chain maps in between dimensions k and k minus 1. What I mean by that is before we pass to the homology, we just had chain complexes and chain maps. So what that means is you're going to have 0, ck, ck prime, ck double prime, 0, and remember phi goes here, psi goes here. These are not the induced maps on homology. These are parts of the chain maps themselves. And then ck minus 1, phi k minus 1. Everything is repeated at the k minus 1 level. And moreover, you have boundary maps. This is for C, this is for C prime, this is for C double prime. So these are the boundary maps of the chain complexes. And of course, this is a thing that goes on and on and on. There's the k plus first row above the picture that I've drawn. There's a k minus second row below the picture I've drawn. We're not going to need those yet. Okay, so the goal is to start with something in the homology on the upper right and end up with something on the homology of the lower left. And this is where the name snake lemma comes from. Our snake is going to wind its way through this grid of vector spaces and linear maps. By the way, the definition of a chain map is each of these squares commute. That's what I want to say. Each of these squares that you see with phi and d, and then the other one with psi and d prime and d double prime, all of these commute. Okay, so what we want to do is send gamma in the kernel of dk double prime to some dk gamma in the kernel of dk minus 1. So dk minus 1 is this map. Well, I haven't shown the image of it, but that means it's at least in the kernels, and then later show that this is well defined up to choices in the boundary. Okay, so that well-defined part we're not doing. I'm only doing the part in red. So start with something which is here. So there's gamma in the chain group CK that happens to be in the kernel of dk double prime. So let's do this there's 4 steps. So start with pick any gamma in the kernel of dk double prime, which of course is a subspace of ck double prime. Okay, now you note that because the top row is exact, so the kth row, the top row is exact. CK, the psi k is a surjection. right? So exactness actually gives us a few things. It gives us the phi k is injective, psi k is surjective. Similarly, phi k minus 1 is injective, and psi k plus 1, say k minus 1 is surjective. So we have that information. Okay, so we have something living in ck double prime, which is our gamma, and our top row is exact. So psi k is a surjection. That means there's something in ck single prime. We may not know what it is. There may be several choices, but there's some beta that gets mapped onto gamma. So there exists beta in ck prime satisfying psi k beta equals gamma. Okay, now we have something beta that gets sent to our gamma living in ck prime. There's not much you can do with it on the left, right? Phi k is an injection, but you have no idea whether you'll actually hit beta or not from the image of phi k. On the other hand, there's a map going down, and that one you can always use. So this beta gets sent to, let's just call it dk prime beta. That's the chain that it gets sent to under dk prime. So note, beta is sent to dk prime beta in ck minus 1 prime. And what's more important is that this dk prime beta satisfies a nice relationship with the map that's going out. And we claim that psi k minus 1 of dk prime beta is 0. Okay, so we have to sort of explain why we are saying that psi k minus 1 is going to send dk prime beta to 0. But this is because psi is a chain map. So if you go back up, beta gets sent to gamma by psi k at the top row. Gamma gets sent to 0 because we assumed it was in the kernel of dk double prime. So gamma is being sent to 0. So if you go right and down, because this diagram commutes, that's the same thing as going down and right. So we know that psi k minus 1 has to send dk prime beta to the same thing that the right and down composition did, which means that dk prime beta is in the kernel of psi k minus 1. So dk prime beta is in the kernel of psi k minus 1. Okay, let's say a bit more. What happens next is the bottom row is also exact. The k minus 1 row is exact. And if you have something that's in the kernel of psi k minus 1, it must also be in the image of phi k minus 1. So our chain dk prime beta is in the image of phi k minus 1. Now, phi k minus 1 is injective. So if you're in the image of phi, there's only one thing that that could be in ck minus 1 that's getting that's getting sent to dk prime b. Which is to say, there exists a unique alpha in ck minus 1 satisfying the relation phi k minus 1 alpha equals dk prime beta. So this alpha is one step to the left of our beta. It's over here. So let's go back to the diagram and see what we did. We started from this gamma in the upper right corner. Then we made a little detour to beta. Then we went back here, went down to dk prime beta. And then because it gets sent to 0 on the right and we have exactness of this row, we were able to produce a unique thing, alpha on the left. So things that we haven't, so we have found something in the lower left corner from starting with something in the upper right corner. And this is the map, dk, that we were trying to build. dk gamma equals alpha is a well-defined map on homology and does not depend on the choice of beta. What I mean by well-defined map on the level of homology is if you took gamma on the upper right, so first of all, I'm saying that alpha lies in the kernel of dk minus 1. Secondly, if you perturbed gamma, if you added something in the boundary of dk plus 1 double prime to gamma and did this process, you'd find something whose difference from alpha was again in the boundary of dk. So sending this kernel object to this kernel object is giving you a well-defined map on homology. And remember, when we found beta, there was nothing unique about it. You have a surjective map, so there could be tons of things that are getting sent to gamma. The point is that whichever one you choose is not going to matter. You're going to get the same homology class on the lower left. So this is the snake lemma, and the proof is these steps. I guess we should make for the assignment of dk gamma equals alpha. It's not, like I said, the most enlightening proof. You just sort of grind through the algebra. But in the next couple of lectures, we're going to see some absolutely amazing consequences of the fact that dk exists, that a connecting homomorphism exists that lets you connect all these homology groups into a long exact sequence. It's going to let us make some very, very interesting derivations.